All right, welcome to section 1.2. In this section, we're going to formalize the process of reducing a matrix to its echelon form. And we're also going to introduce some important vocabulary. Really, the concept is more important than the vocab word itself. But these vocab words are going to get used so much that you'll really want to have them burned into your brain. Okay, so let's pick up kind of where we left off. We had this idea of taking a system of equations and turning it into a matrix and doing some stuff to it to help solve the system. So let me just kind of remind you of the process that we talked about. It was basically a three-step process. It was kind of put zeros below the diagonal, put ones on the diagonal, and put zeros above the diagonal. This is the little more formal, written out five-step process that your book has. And we'll talk through that in a minute. But let me go ahead and get an example up here. So let's say we have some system of equations, three variables. The variables can be A, B, C, they can be X, Y, Z, they can be X1, X2, X3, which is what they'll usually be in our book. It doesn't matter. And we already know that we can strip away the A, B, C equal signs and just write it down a little more compactly in matrix form. Usually they put some sort of brackets around the matrix like that. And then we start doing, these things called row operations. And this is where the forward phase here, step 1, 2, and 3, where those come in. And we will want to try to put a 0 in that spot right there as our first step. And we'll probably do that by adding -1 of the first row to the second row, which will clear out this spot and it will change the other spots somewhat. And then we'll proceed to try to put a 0 in that spot. And then for this matrix, our last one would be trying to put a 0 in that spot. And we'll go on from there. So it turns out as you proceed on doing that and putting zeros in those three spots, you get this result. So just to lock in some of the words that we're going to be using here, over here, this is a matrix. It's an augmented matrix, actually. So keep in mind, augmented means you have not just the coefficients from the left side, but you also have the equal sign right side. So this is a matrix, and more importantly, let's go ahead and call it an augmented matrix. Now this form right here, we've done the forward phase. We've done steps 1, 2, 3, and 4. And this is called row echelon form. Echelon just means like stepwise. So it's kind of this idea of this triangular step over and down. Doesn't matter. You'll see some books and some calculators abbreviate this as REF. And from here, we could go back and solve this system of equations by putting the A, B, C, and equal signs back in. Notice this last row down here would simply become 0A, 0B, so we can ignore those. It just says 3C equals 6, which makes it pretty easy to say, well, C must be 2. And once we know that C is 2, we could go back here and say, now let's do this equation. It's -B minus 3C, which we know to be 2, equals -16. So then we can solve for B, and then we can back substitute again and solve for A. That's all well and good, but if we do this step 5, the backward phase, which is putting zeros above and putting ones on the diagonal, we can go one more step here, and we can get this. This is called the, here, let's kind of make a little, this is called the reduced row echelon form. And the abbreviation for that, surprisingly enough, is RREF. And notice the reduced row echelon form makes it really easy to go back and solve the original system of equations, because this bottom row here now says 0a plus 0b plus 1c equals 2. So really this bottom equation translates into c equals 2. And this equation translates into b equals 10, and this one translates into a equals negative 5. The solution is just sitting right there. And you can go back and plug those numbers into the original and check and make sure that they work. But really, as we move on, if we have all numbers, we are going to typically let a calculator of some sort do this. And if the calculator is doing the grunt work, why not have it go all the way to RREF? Even on tonight's homework, though, there are going to be matrices that we need to reduce that have letters in them. And the calculator can't handle that. So we will need these skills. So on tonight's homework, I still want to see you do augmented matrix, and I want to see you do the steps to get to REF, and I want to see you do the steps to get to RREF as well. And I'll do an example in the next video. But here we're just kind of focusing on big ideas and a little bit of vocab. And there's two more really, vocab words that I want to give you in this video. So I want to point out this idea of a pivot position. Pivot positions are the positions that have ones in the RREF. So I don't like yellow. Let's go. So there'll be there, there, and there. Those are the ones in the RREF form. And those pivot positions are the same no matter where you are within this process. So going all the way back to the original matrix, I could say this is a pivot position, this is a pivot position, and that's a pivot position. So yeah, but those pivot positions are simply where the leading one in a row of the RREF form lives. It didn't happen in this particular matrix, but there could be another one, of course. So it's just the leading one, the first one as you go left to right. So if this negative 5 had been a 1 instead, that's not a pivot position. It's just the first one as you go across each row left to right. I'd also like to throw in the idea of a pivot column. And don't get stuck here, but that's a column that contains a pivot. I know, shocking. So we have 3 pivot columns. Obviously the pivots are here and here and here. If you look back at the original matrix, you would say the first 3 columns happen to be the pivot columns. The fourth one is not a pivot column. And this maybe seems like, well, of course it's always going to be the first 3 columns. That's not always the case. So we'll look at some other examples where it doesn't come out quite so nicely. But this idea of pivot position and pivot column seems really simple. And I'm going to say we're going to pack so much more meaning into it. So the more that you can just really burn this idea into your brain, tattoo it on your forehead, whatever, of pivot positions and pivot columns, what those mean, we're going to just bring so much information out of that idea as we go on in the course. Okay, one more thing to drop into your brain before we finish this video. I just want to point out that the row echelon form is not unique. In other words, when you start with a matrix, you can get to different row echelon forms. The one I have here is row echelon form. It meets these first 4 steps to get REF. This one's RREF. And I could have different versions that fulfill these first 4 steps. Matter of fact, if I just decided to multiply this third row by 2 for some reason and got 6, 12 instead of 3, 6, that still meets all the steps of row echelon form. So row echelon forms are not unique. The reduced row echelon form is unique. When you go all the way and finish step 5, this is the only result you can get. There's a proof of that in Appendix A in your book. If you're really curious about it, I'm not going to take the time to prove it here. But there are some homework questions that ask about that. Okay, so in the next video or 2, we'll get into some little more computational examples, but this has been your daily dose of concept and vocab.